In this section, we are going to explore the fascinating world of molecular geometry and chemical bonding, focusing specifically on three important molecular systems, namely ammonia, water, and hydrogen halide, more specifically HF. Understanding these molecules is crucial as they serve as fundamental examples of how atomic orbitals hybridize to form molecular bonds, and also how electron arrangements is going to influence molecular shape and properties. The first molecule that we have is ammonia. Let's first draw the electronic configuration of nitrogen. Nitrogen has got a total of 7 electrons, and therefore its electronic configuration should be 1s2, 2s2, 2p3. According to what we have here, the 2s orbital is completely filled, and each of these 2p orbitals has got 1 unpaired electrons, which means it is able to form 3 bonds. But if this is going to be the case, then the bond angle should be 90 degrees. Now, when we look into the structure of ammonia, what we see here is the bond angle is 107.3 degrees, which means it is closer to the bond angle of what we see in the tetrahedral arrangement, which means nitrogen needs to undergo sp3 hybridization. Here, for the sp3 hybridization of nitrogen, one s orbital and then 3 p orbitals are going to hybridize together to form 4 sp3 hybridized orbitals. Let's draw the 4 sp3 hybridized orbitals. Now we need to fill all these 5 electrons, total of 2, and then here we have 3, so that's going to be equivalent to 5 electrons. All these 5 electrons in these 4 sp3 hybridized orbitals, which are going to be degenerate. When we say degenerate, they are going to be having exactly the same energy. Right? So what we do is we are going to fill each of these orbitals at least with 1 electron each, and then we are going to start the pairing. Because we have already filled 4 electrons in each one of these orbitals, the first orbital is going to be paired, which means this is the one that's going to exist as lone pair of electrons, which we see in nitrogen. Now the remaining unpaired electrons are going to form bond with 3 hydrogens, 1 each. Right? So each of these unpaired electrons is going to try to form a bond with these hydrogens. Basically, they are going to form sigma bonds here. On the whole, we can see that ammonia is going to have a tetrahedral structure where the bond angle is going to be 107.3. It's slightly lesser than what we see in the regular tetrahedral structure, which is going to be 109.5. And the reason for this is the lone pair is going to occupy more space, because of which all these bonding pairs need to come together with a slight decrease in the bond angle. In the case of ammonium ion, this is going to be a perfect tetrahedral structure where the bond angle is going to be 109.5 degrees. Now, the reason for this is we don't have any lone pair of electrons, which is going to demand so much of space. And all of these are going to be simply bonding pairs. Let's go on to our next molecule, which is water. We'll draw the electronic configuration of oxygen. Oxygen has got 8 electrons, and therefore its electronic configuration should be 1s2, 2s2, 2p4. Here again, we can see that the 2s orbital is completely filled, whereas the 2p orbital is partially filled. When we look into the structure of water, we can see that the bond angle here is 104.5, which is again closer to that of the tetrahedral arrangement, which means this oxygen here should also undergo sp3 hybridization. So 1 s orbital and then 3 p orbitals, they are going to combine together to form again 4 sp3 hybridized orbitals. So let's draw the 4 sp3 hybridized orbitals, and again which are going to be degenerate, meaning that they are going to have exactly the same energy. Now we have a total of 1, 2, 3, 4, 5, 6 valence electrons, and we need to fill these 4 sp3 hybridized orbitals with these 6 electrons. So first we are going to fill each one of these orbitals with at least 1 electron, and then we are going to start pairing. We have used 4 electrons, now we have to use the remaining 2 electrons. These 2 are going to correspond to the lone pairs that's present on oxygen, what we have here. And then these 2 unpaired electrons are going to form bonds with 2 hydrogens. They're going to be basically sigma bonds. And here, the reason why the bond angle is 104.5 is because there are 2 lone pairs of electrons, and these lone pairs demand so much of space in order to avoid repulsion. So therefore, these bonding pairs need to come together in order to make the structure valid, or to allow more space for the lone pairs. Let's go on to the next molecule, which is going to be an hydrogen halide. And we can take any of these halogens, fluoride ion, chloride ion, or bromide ion. Let's draw fluorine's electronic configuration here. So fluorine has got totally 9 electrons, so it's going to be 1s2, 2s2, 2p5. So here again, fluorine is going to undergo sp3 hybridization. So this 1s orbital and these 3p orbitals are going to hybridize together to give us 4 sp3 hybridized orbitals. Now we have a total of 1, 2, 3, 4, 5, 6, 7 electrons that needs to go into these 4 sp3 hybridized orbitals, which are degenerate. So which means we are going to fill each of these orbitals with 1 electron each. And because we said 7 electrons, now we are going to start pairing it up. The first 3 sp3 hybridized orbitals are going to be paired, whereas the last one with its unpaired electron is going to form a bond with hydrogen. And this is the bond that you're going to see, and this is going to be a sigma bond, and all of this is going to be lone pairs that will be existing on fluorine. As we go from HF to HI, it's very clear that the bond length of the hydrogen-halogen bond is actually increasing, whereas the bond strength is actually decreasing. And what is the reason why bonds get longer and weaker as we move from HF to HI? Now we have to think of atomic shells like layers around the nucleus. In the case of fluorine, the bonding electrons are actually in the second shell. So this one, it's in the second shell. And for chlorine, it's in the third shell, and this is in the fourth shell, and this one right here is in the fifth shell. When bonding electrons are in shells that is closer to the nucleus, like what we see in the case of fluorine, they are more concentrated in a smaller space. This is going to create a stronger and shorter bond with hydrogen, such as what you see in this picture right here. As we move to bigger atoms like chlorine, bromine, and iron, the bonding electrons are in outer shells. They're going to be spread out over a large space because they are farther from the nucleus. Because the electrons are spread out, they are going to be producing weaker bonds. So therefore, when you have a bigger atom, the bond is going to be longer. It's more like trying to hold hands with someone. The closer you stand, like in the case of HF, the stronger your grip can be. The farther apart you stand, like in the case of HI, the weaker your grip becomes. This is the reason why HF is the strongest and shortest bond, whereas HI has the longest and weakest bond among the hydrogen halides.